Okay, on to our last topic for this week, which is differential equations. Now, we've already seen some differential equations in the first part of today's lectures, but let's make a slightly more formal definition. We're going to say that a differential equation is an equation that describes the derivative, or possibly derivatives, of a function that is unknown to us. So, for example, we could look at this equation here. dy by dx is equal to x sine x. That's telling us about the derivative of some function y, but we don't actually know what y is all about. Now, it's worthwhile thinking about how one comes up with differential equations. We've said that they come up in lots of different situations. So here's a chance for you to try and figure out some DEs for yourself. So from now on, I'm mostly going to call differential equations DEs because it's quicker. So take a moment and think how you would describe mathematically each of these situations. And when you're done, come back and we'll talk about it. Did you do this? I hope so. Okay, let's talk about it. So if we think about question A, the population of a town grows continuously at an annual rate of 1.25%. So the trick when you're thinking about how to model something with an equation is to look for words like, for example, rate, because that's going to tell you straight away, you know that you're going to be having a derivative somewhere in there, because remember, a rate of change is a derivative. So we want to be modeling the population of a town over time. So that tells us that we've got two variables. We've got the independent variable, which is time, and then we've got the dependent variable, which is the population. So let's just make a note of that. So we've got time, which is our independent variable, and population, which is our dependent variable. And now we should probably pick some notation because we don't want to be writing this the whole time. I'm not going to be super original here. I'm going to use a little t for time, and I'm going to use a big P for population. And just to make sure that we know that our population is a function of time, I'm just going to write it explicitly like that. Okay, so now we need to think about what the sentence is telling us. So the population grows at an annual rate of 1.25%. So something I think is always kind of useful to do is to transform percents into just ordinary decimals. So this will be a 0.0125. Okay. So if it's a rate, so we have a rate of change of our population, so that's going to be dp by dt. And what is that rate? Well, it's 0.0125 times whatever the current population is, because it's changing at a 1.25% of the current population. So we just go and write down straight away 0.0125 times P of t. It didn't even really occur to us to wonder whether we should have a plus or a minus sign here. But if you think about it, your population is growing, so it's got to be getting bigger. So it must be that your rate of change, your derivative, is positive. And if you look at what we've got, here we've got a positive, and because our population is measured in actual positive humans, that's also positive. Okay, so that makes sense. How about B? So B says a radioactive sample loses mass at a rate of 5.6% of its mass every day. Okay, so again, let's just make a note. We're going to measure time, and this is going to be time in days. I'm going to use the variable t, and I'm going to say our mass, and we don't know what it's measured in, that doesn't matter. I'm going to measure that in, I'm going to use the notation m of t. So how do we put together a differential equation for this? Well, it's losing mass at a rate, so that tells us that we've got a dm by dt, and we also know that it is losing mass. So this tells us that overall, if we were to sketch a function of the mass, we might not know exactly what that function looks like, but we know that it must be negative because the mass is going down. So we're almost certainly going to need a minus sign here for our derivative. Now we want to think about it's losing mass at a rate of 5.6% of its mass. So that means over the space of 1 day, the amount that it goes down is 5.6% of whatever it was at the start of that day. So what we must have is that this is 0.056, because that's 5.6%, times whatever its mass was. And again, you can check that this will actually be negative because mass is positive, 0.056 is positive, so with our negative sign, we've got something that's decreasing. Okay, now we've got a bank account that continuously earns 4% interest every year, and at the same time, every year we withdraw $1,000. All right, so let's use some notation. So now we're going to have our time, and this is measured in years. And again, use t, and I'm going to put, and it's the balance that we're interested in our account, so I'm going to call that b of t. And we want to think about how that balance is changing over time. Well, let's start with the interest. So if we were just earning interest, then we know that we'd gain 4% per year. So if it was just that we had interest, we'd have 0.04, which is 4%, times whatever we had in our account. But also each year, we are subtracting off $1,000, which we take out. So if you think about the change in our balance over a period of a year, we're going to gain 4%, but we're also going to lose $1,000. And here, we can't really tell whether our balance is going to go up or down because we don't know what our initial balance is. So if the balance is several $1 million, then 0.04 is a lot more than 1,000, so it should go up. But on the other hand, if we only have $1 in our bank account and we're trying to withdraw 1,000, it's definitely going to go down. So here we have an example where we don't know whether our rate of change is positive or negative. All right, let's have a look at D. So we've got a cup of hot chocolate. It's sitting in a 70-degree room. In case you are wondering, this is Fahrenheit. Otherwise, that would be kind of crazy. Okay, the temperature of the hot chocolate cools, okay, so it's going down, by 10% of the difference between the hot chocolate's temperature and the room temperature every minute. Okay, so again, we've got a rate of change over time. So we've got time, and this time it's measured in minutes. Let's keep that t. And I'm going to say we're wanting to find out about the temperature of our delicious hot chocolate. Let's call that big T. So we've got big T of little t. And we want to know how the temperature of our hot chocolate is changing over time. So let's read this carefully. It's 10% of the difference between the hot chocolate's temperature and the room temperature. Okay, so what we need is the difference between our hot chocolate, which is presumably hotter than 70 degrees Fahrenheit, and the room temperature, which is 70. So that gives us the difference, and what we're told is that it cools, so it goes down by 10% of that difference. Okay, so we've got to have a negative, and then we've got to have 0.1. So that tells us that every minute our hot chocolate is going to get cooler by 0.1 times whatever this difference is. And this is actually part of Newton's law of cooling, which really kind of makes sense if you think about it, because as our temperature of our hot chocolate approaches the temperature of the room, it's going to stop getting cool. So it's not going to keep getting cool, it's just going to get cool until it actually gets to the same temperature as the room, and then it just stops. Okay, so that kind of works. And now let's look at the opposite direction. So now we're thinking about a can of cold soda, and it's sitting in a 70-degree room. So it's presumably cooler than 70 degrees Fahrenheit. And our temperature warms continuously at a rate of 10% of the difference between the soda's temperature and the room's temperature every minute. Okay. So we've got our time in minutes again, and we've got our temperature, which we're going to measure with a big T. And we want to have big T by d little t. And again, we're thinking about the difference between our soda and the room temperature. And this time I'm going to write it as 70 degrees minus whatever the temperature is, because I want this thing to be positive. And I'm assuming that my soda is cool and it's gradually heating up. So this term here is going to be positive. How much is it heating up? Well, again, it's 10%, so it's 0.1. And if we think about, is this going in the right direction? Yes, because we've ensured that we've got both terms are positive, this is going to give us a positive rate of change. So again, the temperature is going to go up for this one, but as the temperature of our soda reaches the temperature of the room, it's going to, our rate of change is going to approach 0, because it's going to be 0.1 times, well, in something very close to 0 here. So it'll be a very small rate of change, so it'll approach 0. Okay, so this is just to give you some practice for taking word problems and turning them into differential equations. Do a little bit of practice on that because it's kind of handy, and actually mostly that's the hard work when it comes to differential equations, is finding the appropriate equation for whatever it is that you're working on. Once you've got the equation, the techniques are pretty straightforward. Okay, so finding solutions to differential equations. So we talked a little bit about this. We want to find the unknown function whose derivative we know all about. So let's start with an example, dE. So we've got dV by dt is equal to 1.5 minus 0.5v. And we're going to say this is describing the velocity and how it changes as a function of the velocity of itself. So the thing to notice here is we've got dV by dt, and over here we've got a v. So take a moment to figure out for yourself which of the following functions are solutions of this differential equation. So remember we talked about how to check that. You plug in your velocity and check that if you take the derivative, you get the same thing as you get on the right-hand side if you plug it in. So I think if we take the derivative of our first, of a, then we would get 1.5 minus 0.5t. And if you plug that in, so we get that on the left, on the right-hand side, we get 1.5 minus 0.5 times 1.5 minus 0.25 t squared. And if you check that, you'll see it doesn't, this, which is our right-hand side, doesn't equal this, which is our left-hand side. Okay, so that one doesn't work. If you plug in just that our velocity is equal to 3, the derivative of that is 0, which would mean that we'd have to have minus 1.5 minus 0.5 times 3, which is 1.5. Okay, so that one is valid. If you do a check, then you should find that B is also valid. And in fact, anything which has some constant over here is going to be valid. So what we can see here is that actually we've got infinitely many possible solutions to this differential equation. And this shouldn't really come as a surprise, because when we were integrating, i.e. finding things which gave you the derivative that we knew about, we found an infinite family. We found the indefinite integral. And that is essentially what we're doing here. We're finding the function that you have to differentiate so that you get this thing over here. Okay, so what we can see is that if you have a differential equation, it has a family of solutions based on, and there'll be some constant which can take on infinitely many values. So if we have a look at the one we've just particularly looked at, in fact, our value of c is very connected to what we call the initial value of our dependent variable. So in this case, it's v0, and you can see that if we plug, so here's the solution that we're interested in. If, for example, so if we look at what our initial value is, so we're thinking of initial because mostly we're looking at time and we're looking at t0, at the time is equal to 0. If we look at v0, then we're going to get 3 plus c e to the minus 0.5 times 0, which is just 3 plus c, because this term over here is equal to 1. So depending, so we have, just to make this absolutely clear, depending on what our initial velocity is, that will give us a particular value of c. So if we have a little bit more information, if we know how fast our thing is starting off, then we can pick which of the family of functions we're actually working with. But if we don't have that information, then we just say, well, it's one of these many values. And depending on the values of c, you get quite different looking graphs. So here's a value of c is equal to 3. But if you plug in minus 3, you get something like this. And if you think about what this is saying that if you start with an initial value of 0, then you end up getting an increasing function like this. On the other hand, if you start with an initial velocity of 6, then you're going to get a decreasing function. So our differential equations can actually describe quite a large variety of behaviors, all in one quite simple equation. And then depending on any additional information that you have, you can pick out which one of the possible solutions it is. So if we're given that little bit of extra information, which tells us about the value of our function that we're looking for initially at v equals 0, then we have what's called an initial value problem. So an initial value problem consists of two things. It consists of the differential equation, which describes our system, and the initial value of that system. So you solve the differential equation, you get a family of solutions, and then you use this point to pick out which of those solutions actually applies in your particular situation. Okay. So just a little bit of terminology. There's plenty more, and if you go on and do courses in DEs, you'll find out more. But things that are pretty important to know, and you'll need if you ever use DEs in anything that you do from here. The first is we classify our differential equations according to the highest order derivative that occurs in the differential equation, and that's called the order of the differential equation. So for example, this bunny over here, the highest order, in fact the only order here, is a first order derivative, the first derivative. So this will be a first order equation. Whereas over here, we've got a second derivative, so this will be a second order equation. And you can get way more complicated than that, so you might have, for example, d cubed x by dt plus, I don't know, dx by dt equals cosine. So you can have different derivatives. You don't just have to have the one like we're seeing here, but in this case you just look for the highest one. So this bunny would be a third order. One other thing that we sometimes use for classifying DEs is we have a look and we see which variables can we see on the right hand side. So we've got our derivative sitting on the left, and you look at the right, and notice our derivative tells us that our dependent variable here is v, and our independent is t. And if it turns out that our derivative is only a function of the dependent variable, then we call it an autonomous differential equation. So this one that I've been doing lots of circling over here is autonomous because if we look at the right-hand side, the only thing we see, the only variable that we see is a v, and v is our dependent. On the other hand, if we have a look at this differential equation, notice that we've got our independent variable putting in a showing over there, so this bunny is not autonomous. Okay, and this is going to be a relevant thing to know because it gives you a hint on how you might solve these equations. So before we dive into techniques for actually solving differential equations, it's worthwhile to have a way of figuring out quite a lot about what the solutions look like without actually figuring them out. So we want to have a kind of visual idea of the sorts of things that we might get for our family of solutions for the differential equation. How do we do that? Well, let's look at an example. So we're looking at the differential equation dy by dt is equal to t minus 2. So if we think about this in terms of the classification we've just learned, the highest order derivative here is 1, so this is a first order. Is it autonomous? Does it only have y's on the right-hand side? Absolutely not. In fact, it has t's, so it's not autonomous. So that's about all we can tell at the moment. Okay, what are we going to do? Well, we're going to see what the derivative at various different values of t tells us about the function itself. So we're going to have a start by looking at when t is equal to 0. So when t is equal to 0, what's my slope? Well, I plug in t is equal to 0 into my differential equation, and that will tell me that I have a slope of minus 2. Now, if you think about what t equals 0 means for our function, it means that for our function, we're looking at values of y that are lying on the y-axis, because that's when x is equal to 0. So let's pick, for example, y is equal to 0. So we're imagining an initial situation where our initial value is 0 for our function. What would the slope look like then? Well, we can draw a tiny bit of the tangent. We know what that would look like. It would have a slope of minus 2. So if I think about what a slope of minus 2 would look like, it would be something like that. So I'm not going to make it a very long bit here because obviously our function is going to change, but just at that point when y is equal to 0 and t is equal to 0, that's what the slope of our function would look like. That's what the tangent would look like. On the other hand, if, for example, our initial value was 1, then again we'd have the same slope. So we would have something that looks like that. If our initial value was 2, we'd have a tangent that did that. And if we had 3, we'd have the same thing, going down to minus 1. So what we can do is we can build up a picture of what the function would look like in a little range around t is equal to 0 for different initial values. Okay, what we're going to do? Well, next we're going to have a look at when t is equal to 1. So when t is equal to 1, if I plug that into my differential equation, I'm going to get 1 minus 2, so that gives me a slope of minus 1. And now we do the same thing again. So I'm going to use a different color. Okay, so when t is equal to 1, now I'm looking at y values on this vertical line here, because that's when t is equal to 1, so the possible values of y lie on that blue line. Well, suppose that at that particular point my function has a value of 1. What will the tangent look like? It'll look like minus 1. So again, it's negative, but it's not as steep as when we were at 0. So it'll be something like, oops, that's not great, something like that. On the other hand, if my function value was 1, then I'd have a tangent like so, and a tangent like so. Let's keep going. So now we're going to think about, what about at time t equals 2? Well, when we plug in 2, my tangent, the slope of my tangent is going to be 2 minus 2, so my slope is going to be 0. So let's have a sketch. So now we're thinking about y values that correspond, oops, I got a bit squonk, on that vertical line. And again, if it happens that our y value is 2, then what is our tangent going to look like at that point? Well, it's going to be flat. So it's just that. And in fact, each of these will be flat. One more point. So let's have a look at when t is equal to 3. Then my slope is going to be 3 minus 2, which is 1. So note that now I've got a function that is starting to slope upwards. So again, let's grab a new color. So now we're looking at y values along that line. And again, if it turns out that our y value is equal to 1, then we'd have a slope like so. If our y value is 0, if our y value is 1, or 2, or in fact 3, or minus 1, those are all possible tangents. And you could imagine that you did this for a whole bunch of points. So I'm just going to add in a couple more here. Do I want to do this? So you'd probably get, so everything on this line given this particular function looks like this. We would have all of these. So this is probably starting to look a little bit hideous, but it's actually quite cunning. Because you could fill in values, for example, probably do something when we're looking at, for example, 0.5, you could plug in some more values. So if I had 0.5 in here, I'd have minus 1.5. So that's a slope that's slightly somewhere between 2 and a slope of 1. So something a bit like this, and so on. And how does this help us? Well, the trick is that we can say, okay, suppose I know that my initial value is 1. Then I know that if I leave 1, I must follow this particular tangent. And if I keep going, I'm going to get to the point where I know that I need to follow, for example, this particular tangent. And then I'm going to get to a point where I need to have that tangent and keep going so that I end up being able to sketch roughly what my function should look like. If I was to start higher up, I'd be doing something similar. So again, I'd get a function doing something like so. If I started lower down. And so by following these little tangent snippets that we've put, we actually are able to get a fairly good idea of this family of solutions that we have to this differential equation. And in fact, if you aren't able to analytically solve a differential equation, which sometimes happens, just like there are things we can't integrate, there are differential equations we can't solve, you can numerically work out the solution by doing exactly this with a computer, not with, colored pens. Okay, so just a couple of things about what we've just drawn over here. So let's just bring this picture in here. Actually, I want the whole thing. I want to paste the image. There we go. Okay, so before I drew in the blue line, so when I just had all the little black tangents here, that's called the slope field. It's not particularly an exciting name. it's a whole bunch of slopes, and we call it a slope field because it's basically covering the whole of the plane. And it allows us to sketch solutions for different initial values, as we've seen. Okay, so it's quite fun to just kind of practice this a little bit, and it also gets you thinking about really what it is that your differential equation is saying. So notice we had a very simple one here, where it turns out that our dy by dt doesn't depend on our y. So we had the same slope no matter where on the y-axis we were looking. But you can imagine differential equations where that's not the case, so that you have really some quite interesting and pretty slope fields coming up. So hopefully do some examples of those. Okay, so now we actually want to get down to the nitty-gritty of solving differential equations. Now, for some differential equations, we can actually just use indefinite integration to solve them. So if we have a look at this one, which should not have an s, that should have an x. If we want to solve this, we're going to integrate both sides. Let's see what happens. Well, we know that y is our dependent variable, x is our independent variable, so we're going to integrate both sides with respect to x. So we've got the integral of dy by dx with respect to x is equal to the integral of x sine x with respect to x. Thinking about this thing over here, remember, the indefinite integral undoes differentiation. So here it's saying, what did I have to differentiate in order to get dy by dx? Well, that's kind of a dead giveaway. You had to differentiate y. And over here, we want to find what did I have to differentiate in order to get x sine x. And at this point, you say, oh, okay, fine, I'll go and think about it. Can I do this by I? Nope. Can I do this by substitution? Not really. Okay, so it's going to be integration by parts. Let's just go ahead and do that. So remember, by parts, I need to choose the thing that I'm going to differentiate, which is my f, and I'm going to choose the thing that I'm going to integrate, which is my g. Well, I don't want to integrate x because that gives me an x squared, and that seldom makes things better. So I'm going to differentiate x, and I'm going to integrate sine of x. And so if I take the derivative of f, that's going to give me 1, and I integrate g, and that's going to give me minus cosine of x. Remember, we don't worry about the plus c in this particular case. And so now I know that my integral is going to be f times g, so that's minus x cosine of x, minus f prime times g, and there's a minus there, so this becomes a plus, the integral of cosine of x dx, and we can just finish this off. Integral of cosine is just sine of x, and now finally I need my plus c. Okay, so the indefinite integral does give us a way to solve some differential equations, for example, things like this. But you can imagine situations where we can't use indefinite integration. For example, suppose we were to have something like dy by dt is equal to y times sine of t. Now this we can't use integration for because, as it stands, we don't know how to integrate a y of sine of t when we don't actually know what y is. That's what we're trying to find out. If we knew that, we wouldn't have to do this. So there are lots and lots of different forms that differential equations come in. We've seen autonomous ones, which only have the dependent variable on the right-hand side. We have things like this, which are not autonomous. And the different techniques depend a lot on the form. So we're only really going to look at one particular form, which is for differential equations called separable first order. Okay, we know that they're first order because the highest order derivative is just 1. And we call them separable because we can write the right-hand side as some product of stuff only involving the dependent variable and some product and some term only consisting of things with the independent variable. So the one I just gave you over here is definitely not separable, but if you looked at, oh sorry, yes, it totally is separable. Because we've got, there's our function, that would be our g of y, and this would be our h of t. Okay, so something like that is separable, but if you had something like dy by dt is equal to y plus sine of t, unfortunately that doesn't count as being separable because there's a plus sign here, not a multiplication. Okay, so how do we solve separable differential equations? Well, let's look at an example and then we'll go and do the general case after that. So here's the differential equation we want to solve. We want to solve dy by dt is equal to t over y squared. So the first thing that we're going to do is we're going to take everything involving y to the left and keep t's on the right. So the first thing that we're going to do is multiply by y squared, both sides. So that's going to give us y squared dy by dt is equal to just t. And then the next thing we're going to do is we're going to integrate both sides with respect to t. So that gives us a y squared dy by dt with respect to t is equal to the integral of t dt. So certainly the right-hand side looks peachy. That's going to be a dream to integrate. But what is going on here with this left-hand side? Well, it kind of looks like we could use substitution here. It's not quite the form that we're used to, but what we've got is some function of y times the derivative of y. So we're going to go straight ahead and use substitution, and with the substitution we're going to make, which seems a little weird, but watch how it works, is we're going to say, I'm going to let u be equal to y of t. Seems weird? Bear with me. Okay, so what happens if I take the derivative? Because that's what we do at the next bit for integration by substitution. Well, I get du by dt is equal to dy by dt. So far I don't seem to have achieved anything at all. But remember, we now do the kind of magical multiplying through by our dt. So this tells us that du is equal to dy by dt times dt. And this is exactly what we wanted to achieve, because notice if we now substitute, what we get is so we replace our y with a u, so we get a u squared, and then we replace our dy by dt dt by just du. And so we've just made life a whole lot easier. We can now integrate both sides. They're pretty straightforward. So the integral of u squared is going to be 1/3 u cubed. And I'm just going to put in, we're going to see what happens here. For the moment, I'm going to put this in a different color, because you'll see that in the end we actually don't really worry about it very much. Let's call that C1. And I'm going to integrate t. That's going to be a half t squared plus some constant. Now ultimately we want to have a function of y, so we need to remember to substitute back in, but that's not particularly tricky here. So we replace our y. So we've got 1/3 y cubed plus c1 is equal to a half t squared plus c2. And if you think about it, you want a function of y. Sorry, you want y to be a function of t, so you want to write it in the form y is equal to stuff only involving t's. So let's do some reorganizing. So we've got 1/3 y cubed is equal to half t squared plus c2 minus c1. I'm going to multiply through by 3. And I'm going to just take the cube root. So finally I've got our y is equal to the cube root of 3/2 t squared plus 3 c2 minus c1. And the thing to notice here is that actually this whole thing could just be replaced by a single constant, because c1 and c2 are two constants, so we could just replace it with whatever that is. So we're going to rewrite this as y is equal to 3/2 t squared plus some c. And there's our solution. Pretty straightforward. And this is basically the technique that we're going to use for any separable differential equation. So long as you're able to do your basic integration, you should be able to integrate separable DEs. So let's just rehash in a general case what it is that we did. So the first thing we did was we checked that what we had was a differential equation that was separable. So we needed to be able to separate it into a function of our dependent variable times a function of our independent variable. Once we did that, we divided through by our dependent variable's function and integrated both sides with respect to t. Then we did a little switcheroo and rewrote our left-hand side as an integral with respect to u, just to make life easier. Finished up the integration, and then the final step was to solve algebraically for y, so that we could write y as a function of t. Might not always happen, but usually it's going to. So let's do one final problem. You can break for a moment and see if you can give it a go, and then come back and we'll work through it. Okay, so this is kind of a bit like doing integration when you want to find a definite integral. And remember I said do the indefinite integral first and then plug in. Well, when you're solving an initial value problem, I recommend that, and in fact it would be very hard to do this differently, first just solve the differential equation and then find your family of solutions and then find your specific solution by plugging in the particular point that you have. Okay, so we're going to first start by solving our DE. So we look at it and we say, is that something that I could just integrate straight? No, it's not, because it's got t's and y's on the right-hand side, but it is separable. So I can rewrite this as dy by dt is equal to y times minus 2t over t squared plus 1. So now I'm going to follow my method, which says I need to get the y over onto the left-hand side, so I'm going to divide through by y. And at this point, I hope that a little alarm bell went off that said, hang on, we need to make sure that y is not 0, because if I just divided by 0, then I would have blown up the universe, which would be bad. So I need to kind of make a note for myself here. This is all true, assuming y is not equal to 0. So what we're going to do right at the end is we're going to come back and look at our differential equation and say, okay, what happens if y is equal to 0? Okay. So now let's have a look what we've got. Now we're going to integrate with respect to t. So I'm not rewriting all of this again. I'm just going to plug in some stuff there. And we need to do our switcheroo, which essentially in this particularly simple case is going to give us 1 over u du is equal to the integral of minus 2t over t squared plus 1 dt. All right, all good stuff. So now we need to integrate 1 over u with respect to u. We know that that's the natural log of u, and let's put in our constant here. And now we need to integrate minus 2t over t squared plus 1. And you'll see that if you use the substitution, so I'm going to call it v because I've already used u over here. I'm going to use the substitution v is equal to t squared plus 1. Then we have dv by dt is equal to 2t. So that tells us that dv is equal to 2t dt. So we can actually replace this bit with just dv. So we've got the integral of, don't forget the minus sign, the integral of 1 over v dv. Okay, so that's pretty nice. That's going to give us minus the natural log of the absolute value of v plus some constant c2. Okay, now at this point you might be tempted to stop, but please don't, because our original variables were y and t. So we've done a whole bunch of substitutions here. We need to get our y's back. So we've got natural log of absolute value of y plus c1 is equal to minus the natural log of t plus c2. And if you were to leave it like this, you couldn't really do an awful lot. But now we're going to do something cunning. We're going to redefine our constants. So the first thing I'm going to do is I'm going to take my c1 over to the left-hand side, to the right-hand side. And then I'm going to define a new variable, a new constant called c, such that the natural log of c is equal to c2 minus c1. And you can easily do this because you can make sure that c2 minus c1 is positive. Okay, how does this help me? Well, now I can use my log laws to combine this into a single logarithm. So I'm going to have the natural log of the absolute value of y, and I just realized I should be having a whole lot more going on here with my t's. It was not just t, it was t squared plus 1, t squared plus 1, t squared plus 1. Okay, that's looking a bit better. I'm going to take this minus sign up here, which is going to give me an absolute value of t squared plus 1 to the minus 1, which is really 1 over t squared plus 1. And then I'm going to remember that this plus over here says I can actually turn these two logarithms into a product inside the logarithm. So that's going to give me the natural log of c over t squared plus 1. All right, and now you can see we're getting to somewhere where we might actually be able to solve for y. So notice that this bit here must be positive because t squared is always positive, add 1 is always positive. So in fact the bit inside the absolute value must be positive, so there's no reason we need the absolute value signs. And since that's positive, we can conclude that our c must always be positive because otherwise our natural log would have exploded. Okay, so what we've actually got is the natural log of y is equal to the natural log of c over t squared plus 1. But we must have that whatever is inside our natural logs are equal. So we must have that the absolute value of y is equal to c over t squared plus 1. And I'm not going to go into a really detailed explanation, but if you do a bit of thinking, you can figure out that we can kind of fold in the absolute value of y into whatever our c is. So in fact, we can write this as y is equal to c over t squared plus 1. What do I mean by that? I mean that if our y is positive, then we don't need the absolute values. And if our y is negative, then we could just bring in a negative to handle that when we're describing our function. And so, there we go. We've just solved this differential equation. we have found the family of solutions for that differential equation. We're not quite done though, because remember this was an initial value. So this is the family of solutions. Okay, to find the specific, what do we need to do? All the way back up here, we need to substitute in that at time t equals 0, our y has a value of 4. So we want to substitute in y of 0 is equal to 4. All right, so let's plug that in. So remember, this is y of t is equal to c over t squared. So let's plug in, we've got 4 is equal to c over 0 squared plus 1. So we know that c is equal to 4. So finally, we get that our y of t is equal to 4 over t squared plus 1. And that's our final solution. Okay, have we forgotten anything? So notice this was a pretty long process. There was a whole lot of stuff going on. And what I would recommend is if you ever find yourself writing something like assuming y is equal to 0, just kind of, when you do, put a red block around it, because we actually need to check. Because this whole solution that we found depends on the fact that y is not equal to 0. And if you have a look here, you'll see that the solution that we got is never equal to 0. And in fact, our general family of solutions here, unless we happen to put in c is equal to 0, this is never 0. So the final thing that we can comment on is what happens if our function is just y is equal to 0? Is that a valid solution? So what we ask ourselves is y equals to 0 a solution? Well, if we've got y is equal to 0, then dy by dt is equal to 0. So the left-hand side is 0. And then we get 2 minus 2t times 0 over t squared plus 1, which is also equal to 0. So in fact, if we take the function, the flat function y is equal to 0, that's a valid solution. Is it included in our possible solutions here? Y is equal to 0 is included if we let c is equal to 0. So if we're taking all possible values of c, then in fact we do in our family have the solution for the thing that we left out in the beginning. This was just lucky. It often happens, but there are also times when you'll find a completely different solution. Okay, but we didn't actually need to worry about that because we were doing an initial value over here, so we found this particular solution. Okay, so that was quite a lot of things. Please do work through exercises, useful things to do. Spend some time doing slope fields, because that's going to give you a kind of intuition for how we go from the differential equation to the function we want to find. And then spend a bit of time getting comfortable solving separable differential equations, which is also going to give you practice on integration. So, win-win. And that's that for this week. So in week 4, it's test week. The test will cover everything from weeks 1, 2, and 3. There won't be any new material in week 4, and there won't be any tutorials because there's a public holiday on the Tuesday, and we'll just have the test on the Friday. There won't be a 4:30 or 4 p.m. tutorial. So you've got plenty of time in week 4 to really just make sure that you're happy with everything up to date. All right. See you in week 4.